With that, let's move to the main presentation. I'm very happy to introduce Louis Bayoul, the Director of Architecture and Platform Engineering from TGS, and he is going to give our feature presentation for this week on from on-prem to on-cloud, optimizing HPC and AI applications for Google Cloud. Louis, thanks for joining us.
Thank you for having me. All right, so I'm Louis Bayoul, as introduced. I work for TGS, and I'm gonna start by trying to explain a little bit who we are, because it has changed recently over the last year. Originally, a lot of what I'm gonna present was presented under the achievement of PGS. We didn't rebrand simply, is that TGS and PGS merged last year, and the name of the company surviving is actually TGS. So for those who don't know TGS, we are a data and service company focused on the energy sector. We work mostly with the oil and gas exploration, but also offshore renewable, carbon capture, and a few other venture in the energy area. A large part of what we do is energy data sale and acquisition. We have a large library, and when we say large, it's hundreds of petabytes. And we also acquire and process data from different sources. Some vessels we operate ourselves, or other third-party acquisition. The processing of the seismic data is extremely computationally intensive. We are generally listed in top 500 of the HPC supercomputer for the machines that we use to do this. In what we are going to talk about today, in the general context, there is a lot of things that have been happening in the last few years where people have been achieving a pretty good use case, good efficiency running HPC workload in the cloud. We've been seeing quite a few things making the news, or a lot of customer stories from the different providers about running things 1,000 times faster, or running millions of things, or tens and tens of thousands of instances. And we are one of those that actually did that. We did run workloads that reached 1.2 million vCPUs on GCP in the past. We'll talk a little bit about how we interpreted those achievements and how we actually do this ourselves, and on the general context about what we see as a convergence of HPC and AI. The fact that extreme scale AI workloads are now reaching into problem space that are actually properly HPC problems, gang scheduling, or extremely tight requirement for communication between workloads. And that is actually pretty interesting in the sense that a lot of those AI workloads are born in cloud. They came from the cloud, but are now having HPC problems. And that create demand for our cloud infrastructure to be more HPC friendly. So a little bit of a story, when I say that we used to be listed on top 500, we even ranked 13th when we introduced Able or Cray XE40 in 2015. At the time was 5.37 petaflops, which is not a lot anymore, but it still was a lot at the time. We ran a combination of two Crays. It was attached with 12 petabytes of cluster file system. We had a reasonable or fairly significant compute capacity on premise at the time. Attached to that, we also had community computers, so normal classical Linux clusters that are numerous, but definitely not as performant for what we did at the time. But like everything else in IT, supercomputers have a shelf life, and after a few years, we needed to think about the replacement, we needed to actually get rid of our Cray or find something to do about it. The other thing we are starting to see is that in that context, we've been starting to see and even feel now the slowdown of the Moore law. We're seeing that the performance per dollar per each generation is not necessarily the same as it usused to be. The bump that we see on performance increase are not as linear as they used to be. we also see that this is usually compensated by going toward accelerators. Like GPU has been like a great way for compensating that. But yeah, programming for GPU has been like engineering heavy and quite taxing on like maintaining the same evolution on generation on generation. And also like simply adding more power was not really feasible. Like the power density of the chips that we have now is reaching, yeah, really, really high things when we're looking at CPUs that are in like 300 to 500 watts per chip. This means that getting spaces in data centers that are adequate for that, or like, yeah, is difficult. And when we are working toward like green or even carbon-free energy targets, this is also difficult for us to justify it in some aspects. And we're also seeing that the traditional actors that were driving the high-end compute infrastructure, hardware infrastructure, were actually being displaced. Big tech and the hyperscalers, so the cloud hyperscaler, were like buying so many chips that they became the primary factor for like engineering for the chip provider. The supply chain issues that we've seen in the last few years have been also like making being a lot more difficult to get hardware that was exactly sized and designed for the problems that we wanted to solve in HPC. With that consideration, like PGS at the time was really trying to figure out how to like go forward, and we're starting to see like using the cloud as a potential to not necessarily replace, but at least potentially offset some of the demand for CapEx and some of the like potential for more agility in terms of like benefiting from other things that were developed for needed were tangential or like slightly on the edges of the core of what we were doing. So we effectively started our cloud journey with that idea that the cloud could be like something that could help us, or something that we could use to compensate for some of the problems we're seeing in the industry, in the overall picture. And effectively, what we landed on was an iterative process. We didn't knew it at the time, but we effectively went through different waves of learning and then re-strategizing and focusing on our direction. Some of it was purely knowing new things and understanding better. Some of them were just like external factors that forced us to actually like make choices. So coming all the way back to 2019, we started with that assumption that we needed to understand the cloud better. We needed to try to see if we could use it as a tool to lower our CapEx for next platform replacement. So effectively, whatever was coming after our craze, we wanted to make sure that we could target 80% of its capacity, and the rest will be 20% will be the cloud consumption as a burst model. We effectively did a POC, and that was very much a lift and shift. We took what worked on premise, we dropped it in the cloud, and see how it went. There is no secret there. This wasn't great. It definitely causes a lot of grief. But by 2020, we had learned enough that we knew that there was more than just a lift and shift. We had two things happen to us. The first one was that with the global pandemic at the time, our industry was very impacted. And the CapEx that was actually planned for the Cray replacement was not available anymore. So we actually had to find a way to replace that capacity. So we turn our ambition on its head. Instead of like targeting 20% for the cloud, we try to say, all right, the Cray represents 80%. We'll try to offset the Cray with the cloud. It was kind of a gamble at the time, because for us it was really we didn't knew if we could make it, but we also knew that we didn't have a choice. We needed to find a solution. We called that time a lift and improve, mainly because we took the architecture of the HPC environment that we had on premise and isolated the pieces that really didn't work in the cloud. And we tried to remove those only, so engineer out those and replace them with things that were a bit more adequate. That did well, that did really well actually, because it made it economically viable for us to run. But it also showed that we had significant issues that will actually be problematic for operational and effectively maintenance and overall continuity of service for this. Mainly is that a lot of the pieces that we had to glue together to actually make it work properly in the cloud were not scaling. And the engineering effort to actually like fix those was significant. So by the end of 2020, we had realized that we could make it work efficiently for cost and likely for scale, but that would require effective, properly re-engineering for a cloud-native environment. And this is where we decided to go toward Kubernetes as our orchestration and object store as a primary data input and output mechanism. But after all those efforts, by May 2022, we had decommissioned our craze, and we were running 80% of our compute on GCP. With that success, it was both very impressive in terms of like cost efficiency and on terms of turnaround. The user experience was actually like coming back pretty positive, despite some of the shortcomings that we had to go through because of the aggressive timeline. So it was decided for us to actually focus on going 100% cloud. Interestingly, you can see in the timeline the Pareto principle is that it took us a lot less time to go from 0 to 80% than it did from the last 20%. So never underestimate this. But by 2025, so actually as of last month, we did decommission our original data center that was containing the 20% remaining workloads. Of course, things have changed since then. The merger with TGS actually like quite rightly changed those plans, because we have inherited a lot of new data centers. So we can't now say that we have 100% decommissioned all data centers because we inherited some new, but the plan actually still succeeded with its original terms. So why did it take an iterative process? A few things. There is definitely two sides of it, the technology and the organization. On the technology side is that it took a long time for us to build enough confidence and learn enough so what worked and what didn't work in the cloud to figure out what we needed to do. It also took a lot of time to get the right resources. Finding at the time we were starting this journey, finding people in the industry that had enough cloud experience and also enough HPC experience to understand the problems was difficult. And getting the people from one space to understand the other took a long time. So people needed to learn a lot of things that were basic knowledge in the other industry, basically. But still, that was something that took quite a bit of time. We also had to build a lot of things that didn't really exist. As I mentioned, our time in the lift and improve phase was really showing that there was a lot of things that we took for granted in the like on-premise HPC that were not fitting well in the cloud environment. So we had to redesign a lot of our framework, a lot of our operational methods for like working with HPC workloads. And that took quite a bit of time. And the toolbox is actually different. Like a lot of things that exist in the cloud don't exist on premise or will not make any sense on premise, and vice versa. There are things that you can do that are highly optimized for your on-premise environment that have no equivalent in the cloud. So that has been a learning and something that we had to overcome, and that took quite a few trials, basically. On the organization side, there's a lot of things that actually changed for the business. One of the biggest things was on capacity planning. We actually went from a model where the only capacity planning we do is optimization, is making sure that we run as much as possible from the footprint that we have on premise. And a lot of the capacity planning is about organization and prioritization. So what is going to come first? Do we need to preempt something to actually put something instead? Those kind of things. When we go into the cloud and the available compute is so big that backlog is not necessarily something you consider much anymore, the problem is about cost optimization. And the organization took a long time to actually get used to this. And overall, for developer, it actually has been quite a journey. There's a huge amount of changes that had to be like integrated and understood by the developers. Things like that are like almost a given in the cloud, like going through containerization of your workload, or like using a large set of APIs to actually interface things, are not necessarily things that the HPC world was actually doing in the last 5 years. So getting the actual institutional framework for developing with those toolset took a bit of time. Interestingly, we did have to change a lot of our algorithm, or a significant portion of our algorithm, to accommodate the cloud. But it actually doesn't rate that high in the list of all the changes we had to go through. It is a significant engineering effort, and it's something that we need to recognize. But it is not so different than when you move from a significant hardware platform to another one on premise. You do need to re-optimize your algorithm, and that's more in line with the life cycle of R&D development for HPC. So effectively, what did we learn on the both approach? For us, the lift and shift, the critical learnings were that it was about 3 to 5 times more expensive than on-premise. So it was effectively a no-starter to go at scale for this. We also had problems scaling it. Is that a lot of things that we had that were working on premise had assumption about like things were static, like dynamically provisioning workloads, like infrastructure doesn't really make any sense on premise, and a lot of like tools that we have don't cope well with dynamic infrastructure. The lift and shift experience for the user was really bad. A lot of things that were easy to do in a data center that's co-located don't get easy at all in the cloud environment. Like a lot of like security by default, that is not something we have in HPC on premise usually. And what we realized that it actually had a lot more technical debt, that just making sure that the lift and shift component were able to talk to the cloud were actually like kind of fitting like something, yeah, like that was definitely not designed for it on the side, and we were looking at something that was looking more and more like a Frankenstein thing. What we said is that it could work, but it could not scale, and it will need to be subsidized by on-premise. So like the cost balance basically will need that to make sure that on-premise is cheap enough that we can use the cloud. What we learned with the cloud native engineering is that we can make it lower, or at least the same cost, and fully depreciated on-premise, which was absolutely fantastic for us. The technology scale much better than what we used to on-premise. Also much, like some of the technology scale we can access is also like things that we never thought we could get on-premise. The user experience actually get very good. We can benefit from like modern practices on how to bring like workloads to users that are like cloud native and like cloud enabled. That has helped quite a bit. And it effectively forces us into like a modernization effort. So we actually embrace more industry standard practices, things that are not necessarily like just in the HPC world, but are more generic into the IT industry. So yeah, going a little bit more into the engineering effort, what we actually had to go through. On the one of the big aspects was we couldn't really use a POSIX parallel file system in the cloud. It was way too expensive and really hard to scale. The cloud providers have been working on this for like the last few years, and this is definitely getting better. But at the scale we're reaching, those still stand. It is not something that is as efficient and as and cost efficient and as scalable as Object Store, which is a solution we used. For us, what that meant is that we had to re-engineer our I/O library between all our workloads, so it actually could talk to Object Store. And we had to make sure that we could actually scale. So it was like the scaling patterns for like a POSIX file system and an Object Store are different. So we had to re-engineer a little bit for this. The compute was also pretty expensive. Like in general, you get it's like the hardware you get on premise for an HPC system are heavily optimized for your workload. You actually like know exactly what you're gonna buy for like the actual workload you're gonna run. The cloud is by nature more generic, and on top of that, it's a rented service, so it's something where there is some margin that you have to pay to use. So it is more expensive than what you would actually buy on premise. But by leveraging like preemptible and the spot market, we can actually like make this significantly cheaper than what we were able to get on premise. What that meant is that we had to actually move from like tightly coupled workloads, so leveraging MPI, to like solving our problems in an embarrassingly parallel way for the most time. That actually introduced checkpointing, which is like something we never actually did on premise. So that was some like pretty big effort on this, but it allowed us to like significantly reduce our compute costs in the cloud. For the user experience, mostly we had to figure out how to integrate the on-premise existing user experience with the cloud and whether it was better. This was mostly done by trying to bridge things and leverage what existed already. And this is something that was done by leveraging native technology in the cloud. So like monitoring, we actually try to use industry standard tooling that allow us to do this instead of building things that were homegrown. And we moved toward like using a lot of APIs to actually integrate things and decoupled as much as possible, so we can interface services that are based on different principles. And for the cloud engineering, we realized that at the most possible, we need to leverage things that are managed by the cloud provider when we go into extreme scale. This is a convenience that actually has a lot of value. So for us, for example, moving to Kubernetes meant moving to GKE, so Google Kubernetes Engine, because that meant that a lot of the administration burden and all the extreme problems you get at scale for Kubernetes handled for us. And that meant for the engineering task was to re-engineer workloads so they can actually fit inside Kubernetes, which is mostly using like the job API, the Kubernetes job API, and leveraging services for the ancillary supporting services of our workloads. So why did it make sense? Mainly because that allowed us to remove a lot of things that we didn't need to maintain in our stack. So the value of the cloud, the hyperscaler, is basically like the convenience, the actual services that they provide for your stacks that you don't have to own. And there is a fine line between how well you can engineer something better and how much more efficient you can get, and how much value you get from a service that is like ready and managed for you. For us, because a large portion of our infrastructure wasn't really interfacing well with the cloud, like a lot of the tooling we had were never meant and they were actually designed to use the cloud well. As much as we could offload to the provider and leverage was really value for us. It was engineering effort that we didn't need to make. We also realized that even if it wasn't a hyperscaler like providing managed tool, using cloud native components or industry standard components that were meant to scale in the cloud was a lot better than trying to get something that we used to have scale. We hit hard wall basically trying to get our or on-premise scheduler to actually operate at the scale we wanted in the cloud. So this is the kind of things where we expect that to get better, but we don't expect that to actually like get to the point where things can work as well in one world or the other, because they operate in significant different of like constraints. And the history of both mean that the actual number of features that needs to be covered is too huge for it to be able to cover all use cases perfectly. We learned also that open source and the industry standard tooling is very important. So portability for us was quite important. We didn't know if we were going to need to be in one cloud forever or if we need to expand to multiple clouds. But we also knew that we needed to be able to leverage industry skill set. So if we wanted to onboard somebody, we needed to offer them a stack that was easy to understand, which meant being able to leverage what exists out there that they can have some exposure to. And yeah, using a spot market for us has been a great learning. That we were very reticent initially. The idea that the workload is going to be preempted and might not complete was a worry that we had quite a bit. But we realized with experience that actually it's a lot faster and it's a lot cheaper to restart a few of your workloads than to try to get everything running as stable as possible. So what did we achieve? So on the compute side, we now have an environment and infrastructure that actually can scale from like 0 to 25 petaflops in a matter of hours. So for comparison, our craze were around 9 petaflops. So we did a significant increase. One of the things that people actually like notice when we look at those graphs is that, but your utilization rate is really bad. Yeah, of course. Our average is about 2.3 petaflops. And that means like if we had a 25 petaflop cluster, it would be 9% utilization. But actually it doesn't matter anymore at all, because as we actually only pay for what we use, what actually matters is exactly that. One thing that also is to note is that in that case, our largest job ran in about 15 hours. On premise, that used to take close to 3 weeks. The main reason is not only compute, it's also storage. And we'll see that in a minute. But coming back to the idea that what that kind of workload usage in our cloud would actually look if we had only those 9 petaflops that the Cray used to provide. We can see that, the utilization is not that much better actually. But the backlog and the time to actually complete the workload is getting pretty impressive. And if we go to the extreme, which some people actually like suggest that, okay, you should actually have like your average utilization or like maximize your utilization, which is what we used to do. If we go with our like 3-ish petaflop, which is like close to our average, then the backlog like increase, it becomes 300 petaflop of backlog. And the average utilization goes to 85%, but also mean that the time to completion for jobs becoming like, absolutely huge. And this is something that we have to remind people when we actually look at graph again, is that if we look at the whole in the utilization, what we don't see is the turnaround and the efficiency on compute time that we actually gain. And this is something that has been quite important for us, like to discover. On storage, one thing that we actually got by moving to object store is that access to bandwidth that we didn't thought we could be able to afford on premise. As a reminder, like our Cray was coupled to a Lost-of-File system that would provide about 250 gigabytes a second. On GCS, we get 1 terabyte a second, and we can do that like in a pretty aggressive fashion. The other big advantage behind that is that because we pay for what we use, we don't have to massively over-provision our file system on premise. Like even if you use Flash, in order to provide that kind of bandwidth, you know that you're gonna need to use like a serious number of disks to do that, which means serious capacity. On GCS, we can see that we reach like a few tens of petabytes of data, but those constant data, those crash data, for example, get deleted immediately after. So after a few days, when the job has finished, and we actually go back to pretty much nothing. And on the other end, if we had those like 50 petabytes on premise, this will be a pretty expensive file system, especially coupled with that kind of bandwidth that we require now. On terms of what we actually did, so going a little bit more on technical side. So we now have Kubernetes as our HPC platform. So it is the core of how we run our HPC. All the job orchestration, so the actual workload orchestration is based on Kubernetes job. We have direct integration with the Kubernetes API to drive how the workload is behaving and how it's being provisioned and its entire life cycle. We use an in-cluster Redis database to actually do task persistence, mostly because at extreme scale, it's been a little bit difficult to get the Kubernetes API to do it for us. So it's not necessarily solving all problems. You always have things that you have to handle yourself. And we like run pair namespaces workload, so it's a good isolation for how we do things. We run 12 Kubernetes clusters, so JK clusters. The main reason for that is being able to scale enough. So a single cluster can scale to 15,000 nodes, but we have workloads that leverage up to 50,000 nodes. So we actually spread all different workloads across multiple clusters. And yeah, so coming back to the POSIX to GCS move, it was an extremely big part of the journey. It was difficult in the sense that POSIX has been with us for a long time. We have a lot of habit and reliance on it. So we actually did that by our IO layer is implementing POSIX, but talking object store under the hood. So for developers that actually implement the IO library, they can still use the same calls that they are used to, but the optimization and the actual transport is being done directly through the object store. But it significantly helped because when we ran Lustre on GCP for lift and shift model, running Lustre was up to 40% of the cost of a workload. Which was not sustainable. It's like it never is that high for running HPC workload on premise. And the last bit has been about moving from preemptible to spot VM. And so this is mostly about the optimization for cost. Here we're talking about leveraging the normal 80% discount that you get about on the preemptible and spot market. We mainly had to move away from using MPI. It did add some complexity. So this is where a lot of algorithm needed to be changed in order to accommodate for an embracingly parallel method. It's not always possible. There are definitely HPC problems for which not having tightly coupled workloads will be extremely inefficient. So it's still a problem for those. But we are lucky that in the seismic industry, we can pretty much always use an embracingly parallel solution. I said not always, but almost. And one thing that was a little bit difficult in the early days was to deal with preemption and the actual capacity available for spot VM. One thing that has been great is Kubernetes, or GKE in particular, has mechanism now to actually do node fallback. So you can actually define what your workload is going to be able to run on, and it will try to get it for you without having to engineer how you're getting each type of VMs. So there are tools out there that are helping quite a bit with capacity management for spot VMs. And actually might slide a little bit out of order as I was supposed to be about, but it's okay. Kubernetes has been orchestrated as our native scheduler, and as I mentioned, it was a massive tool for us to replace the on-premise scheduler, traditional scheduler, inability to scale and to handle dynamic infrastructure. So Kubernetes is doing that perfectly well. Integration with the GCP API or other cloud APIs mean that it can dynamically provision nodes without you having to care about pretty much anything. It deals with preemption without any issues. So if a node is reclaimed, you can get another one. It's been it's been fantastic for that. And that's where I'm gonna leave it, I think. So effectively, one of the big things that we learned, and the main thing we learned effectively, is that it allows us to do business differently. We can get a lot more compute at an instant T than what we could actually have with any CapEx that we will invest. We have changed the way the business is actually considering the compute resources. we had a lot of like time where capacity planning was chasing the business to fill the machines. So finding R&D project or finding like potential upsells, which were pretty dodgy, to just make sure that we run 80% of our compute full. And what we notice now is that what we run in the cloud is extremely tied to our revenue. So we're making sure that the cost that we're running in the cloud is actually like bringing revenue. And that is great. And what we also learned in that journey is that the code optimization for a single architecture is actually not the only thing that you can do in the cloud to like decrease the turnaround. Getting more compute, like being a bit dumb about the way you solve a problem, is actually sometimes easier and cheaper than spending like months and months of engineering resources to like fine tune a problem to be more efficient. We also noted that the time that we can take to actually optimize a program need to decrease significantly. Because we're not stuck on a hardware platform for many years, it means that we benefit from the new SKU and the new actual like chip that are being released by the hyperscaler, by the vendors and the hyperscaler like provided for us in a much more frequent basis. Which means that if we expect that a project to get 20% improvement is going to take more than 6 months, we have to weigh that against the like new SKU that is going to come in that is likely to be in that ballpark in terms of potential improvement. And anything that is going to take more than a year is something where it has to really be a significant bump in engineering efficiency to be valuable. And this is me.
All righty. Thank you very much, Louis. That was a great presentation. Lots of good information there. I want to encourage our online attendees to submit questions, and I will also ask some questions as well, Louis. I see a couple of questions in here now. Hold on. Morton asks, would you have migrated to cloud differently today, given your learnings and perhaps also because the cloud has matured compared to when you started? So basically the lessons you learned over the last 7 years, would you do it differently if you did it starting today?
I would say definitely. And there is a simple reason for that is what we did is akin to in the Kubernetes world doing it like the KCI way, the Kubernetes hard way. So you do everything from scratch. You actually like do absolutely everything yourself. And we did that because we didn't have tools and things that could help us do it. We also didn't have an alternative. We had to do it. If we were to do it now, there is a lot of more new tools. And like if you go in the GCP ecosystem, for example, the HPC toolkit is a great way for you to actually like bridge the gap between how you handle your HPC platform on premise and how the cloud actually require you to handle things to be efficient. There's a lot more technology that's much more adequate for like running HPC workloads. We see a much more like cloud-friendly file system, for example, in the cloud than we used to like 5 years ago. So I would definitely do it differently. But one thing that we learned is that there is definitely a 10x difference between like the like effectively the incremental improvement you can make compared to a significant re-engineering that is based on a cloud native principle.
Great. All right. Bill Turner asked a question on the timeline slide. Have you maintained some data center resources to store your data and IP?
Yeah, so data center never die. It's like software. So yes, we do have, so we have HPC data centers and we have IT data centers. Our IT data centers haven't completely disappeared. We are migrating also those in the cloud when we can, but those are sometimes a little bit more complicated than everything. That there are things that are like IP is something, but for HPC, the migration that we did last month actually completed the last data, so live data that were hosted on premise are now hosted in the cloud. So all the campaign storage for all active projects that represent 100% of compute capacity are now 100% in the cloud.
Right. I had a question for you about the file system. You said that several slides ago, you said that you found that using Lustre or using a POSIX compliant file system was not cost effective due to the cloud building blocks for these. Can you dig into that just a little bit? I want to understand if that's still a true statement and for what kinds of I/O constraints or needs of simulation applications and other applications that might be true for, and where it might not be true, where the Lustre and other POSIX solutions in clouds might be adequate.
So it definitely has changed. So giving you some background, when we ran Lustre on GCP in the early days, there was no managed system at all. So you had to build everything out of GCE. This actually showed a lot of problems about the building blocks, a lot of problems. Like the PD, so the persistent disk that you use to build them, the bandwidth you get per PD, for example, is a lot less than what we used to from a storage system on premise. So what you get as a JBird and like a couple of servers on premise is order of magnitude different from what you can get out of PDs. So the overhead that you had for over provisioning and both on disk and on compute in order to attach them made that you had to drag a significant overhead on cost, basically just to get the size and performance you needed. The cloud and like GCP has been doing a lot of effort in that direction, and you can see now that the overhead that you need in order to like achieve the performance and the capacity you need for your workload is a lot less. But fundamentally, you also have a problem that is very hard for the cloud provider to change, is that the POSIX parallel file system that HPC traditionally use on premise are very, very dumb. They don't have a lot of features that. So they're meant to be fast and they're meant to be inexpensive. That's the only thing. And on the other end, the cloud building blocks are already reaching features by default. So you do have some overhead with that. You do have like complexity also that add that. There is a native things in the cloud, which is that you get guaranteed bandwidth. So when you attach a PD to your VM, you know you're gonna get the bandwidth that is advertised. And that engineering has a cost. So there is a lot of things that are potentially advantageous if you know how to use them, or can be a big drawback in terms of cost efficiency, depending on how you actually leverage those. I would say that now that we cross the chasm for us and we pretty much entirely an object store, there's no point to actually like revisit the POSIX parallel file system.
Right.
But if we were starting new, we'll definitely have a mix of those, mainly because when you look at your portfolio of application, you always have a few ones that are actually really important and matters where you can spend a lot of engineering effort. And we have a lot of them that are necessary, but for which like you don't necessarily make a lot of revenue. And the engineering on those will not make a lot of sense. So if we had the possibility at the time, we probably would have kept like a minimal footprint of POSIX compliant file system, just so we don't need to actually go through the engineering on those.
Got it. All right. Now, I want to go back to a statement you made about, and I want to make sure I characterize it right, Louis. You said that the lift and shift was substantially more expensive in going to the cloud. But once you embrace cloud native, the cost was roughly the same or less to use cloud, but that included using spot instances. It included changing your I/O to use object store, et cetera. In doing that comparison calculation and showing that your cloud native version could be as cost efficient or even better as your on-prem MPI Lustre version, did you account for human time on both sides in that? For example, there's really, I think, 3 big chunks of human time. One is the application developer and the human time in developing and running the application. Another is the time in planning the data center upgrades and planning the system things, which I assume that time goes to 0 now, right? You just basically keep track of the evolution of the technologies in a cloud environment as opposed to planning a new data center and planning a new system. Is that accurate? And did you account for that in your cost comparisons?
Yes, and this has been a very challenging topic. When we get into TCO for cloud and TCO for on-premise, we get into apple and oranges territories. It is very difficult to make a one-to-one comparison, but we're using the exact same method to compare. And there is a lot of reason for that, but one of the fundamental one is just that what you used to operate and how you operate don't apply. So you have to change the way your organization operates, which means you have to change the way you actually account for things, how you cost things in order to do things correctly in the cloud. And that has been a very hard learning for us, is that we know now that what we spend on engineering resources on like cloud workload operation is less than what we did for on-premise. But it was really difficult, like, to make that call ahead of time. We, as I said, like in our timelines, that for us it was almost a gamble because we were forced to do the migration. We didn't have the capex to replace or Cray, so we were hoping for the best, and it turned out good. No, we have the learning. We actually like have the proof that we did the right choice, but we didn't have all the facts to actually like make sure that it was the case at the time.
Got it. So you realized some cost savings by switching from parallel file system to object store. You realize some cost savings by using Spot and allowing preempting. There's some human cost savings there as well, at least in terms of the data center and systems planning. And it sounds like there's some in terms of the ongoing engineering effort. Did you also do anything, you alluded to this, but I wanted to know, did you do anything to calculate the cost savings of the fact that you paid for what you used as opposed to paying for a system with a fixed number of cycles available for all time? I think the way you phrased it in your presentation was you didn't have to find research projects to fill up the system anymore. You could map the spend directly to revenue. So I assume do you have any idea roughly by what factor you would have had to over provision an on-prem system to do just the work that you got done in the time in a lumpier fashion in a cloud model?
It's a very difficult one. And the reason for that is like it was ingrained in the business in how people were actually like behaving. A good example, for example, that when we started to use the cloud, we had a very, very strict organizational policy on how to consume the cloud. So anybody that were like creating jobs had a pretty strict approval process to actually like get it done. To the point where if you're like, we're looking at like a few $1,000s for jobs that can cost millions, for example. So we were looking at extremely strict guidelines and guardrails for people to look at how they're gonna do the thing. And effectively, it railed in a lot of behaviors that we took it for granted. Like we took for granted for a while, like doing testing with a very large production data set, or like changing a few parameters, not necessarily knowing exactly what it's gonna do. And just those things, which mean that we don't necessarily run as much, or we're more efficient in the way we actually parameterize our job, meant that our effectively our overhead or actual margin between like our revenue and our cost grew naturally.